So this is going to be a summary of everything to know about integrals from chapter 5. The first thing to make sure you know, probably the most important thing, is the geometric interpretation of integrals. That's probably the most important thing for understanding what integrals are all about. You got a function whose graph might go both above and below the axis, like this, say. Some wild and wacky function. And let me go ahead and label the areas between the graph and the axis. This one's going to be A1. This one's going to be A2. This one's going to be A3. And this one right here is going to be A4. I want to think of these A's as all being positive numbers. Positive areas, as we usually think about areas. If I do think of all those as positive numbers, the integral is A1 minus A2 plus A3 minus A4. Add a positive area when the graph is above the axis, and subtract a positive area when the graph is below the axis. And it's always the area between the graph and the axis. Of course, you also could group together the terms that are added if you like, and also group together the terms that are subtracted if you like. Though if you did that, you'd want to be careful to include parentheses and a plus sign right there, actually. Of course, we also thought about the real-life interpretations of these things. 3 main applications so far. If the horizontal axis is time, if I use t, say, instead of x, and this graph is a velocity, the fact that it goes both positive and negative would correspond to back and forth motion. Say rightward motion when the graph is above the axis and leftward motion when the graph is below the axis. The integral is going to give you the displacement, the change in position. Not the final position itself. This is something I often test on for the mini exam, but the change in position. For the final position itself, you have to add on the initial position. Now, usually that's 0, but it doesn't have to be. And maybe just for making sure you keep on your toes, I might make it something non-zero on the exam. Sometimes you might need to just estimate these areas with, say, boxes. If there's graph paper on here, this is graphed on, you might want to count boxes and calculate the area per box to estimate areas that way. But we also want to be able to do numerical integration with left-hand sums, right-hand sums, and trapezoid rule. If we're interested in the distance traveled in the application, we would want to take the absolute value of the velocity, the speed, as a function of t is the absolute value of the velocity. And if you integrate the speed, you do to get the actual distance traveled. You won't get something negative. When integrating the velocity, you could get a negative number. I mean, it looks like A1 and A3 are bigger than A2 and A4, so I get a positive number in this case. But this is back and forth motion. You could end up to the left of where you started. The displacement could be negative. You want to be able to allow for that and be able to detect when that happens, so to speak. If you were going to graph the speed, it would be the same as the graph of the velocity when the graph is positive, but when it's negative, you would have to reflect that part across the horizontal axis. So those blue curves correspond to reflecting these pieces across the horizontal axis to get the graph of the speed. And yes, you should know that technically speaking, just like with derivatives, integrals really are dependent on the limit concept. With derivatives, slopes of tangents, they are limits of slopes of secant lines, lines between 2 points in the graph. Let one of the points approach the other point effectively to get the slope of a tangent. That really defines the slope of the tangent when that limit exists. With integrals, well, it's trickier. They are limits of Riemann sums. I'll write a right-hand sum here. A limit as n goes to infinity, as the number of rectangles goes to infinity, because they're all getting skinnier and skinnier, of, say, a right-hand sum, f of xi times delta x, where delta x is b minus a over n. That's the length of the interval divided by the number of rectangles. And xi is a plus I times delta x. If I'm starting I at 1 and going up to n, that corresponds to a right-hand sum. Letting n go to infinity makes all the rectangles skinnier, and there are more of them. There are always n rectangles. Does this limit exist? If it does, and it will if your function is nice, like a continuous function, then the limit will equal the integral. That's not really a definition of the integral, because with the definition of an integral, you want something more robust. You want the limit of right-hand sums to be the same number as the limit of left-hand sums and the limit of midpoint sums and trapezoid sums and Simpson's rule, and even more arbitrary sums, where maybe in each interval you don't use the left endpoint or the right endpoint or the midpoint, but a random point to determine the heights of your rectangles. And maybe you even allow for rectangles of varying widths. Yikes. If you want your theory to be robust, strong, you would want the limit of all those kinds of Riemann sums, as all the rectangles get skinnier and skinnier, to be the same number for the integral to exist. That's the concept of integrability. Do you have to know that for the exam? No, I'm just telling you, I'm informing you about it, okay? Math majors have to know a bit about that for their senior level real analysis class, but you won't have to know all those details. But you should know when you've got a nice function, this will still be a true equation. Figuring out formulas for these summations is very difficult in general. But if I give you a formula for the summation in terms of n for a particular f, then you should be able to take the limit if it's a simple enough situation like we saw the other day. But finding formulas for the summations, that's a tricky thing. Okay. So mostly we want to avoid this, though we don't want to forget it. Though, as I hinted at, you should be able to compute right-hand sums without a limit sign for any particular value of n, or a left-hand sum where I goes from 0 to n minus 1, or both, and then average them to get the trapezoid rule. But mostly, we are happy to use the fundamental theorem of calculus. FTC is your friend. What's the FTC? It is a theorem, fundamental theorem of calculus, if little f is continuous on a closed interval and capital F is an antiderivative of little f on that same closed interval. So what does that mean? That means the derivative of capital F at any value of x in the interval equals little f of that value x for all x in the closed interval. Now, it's a little weird here because being a closed interval, you got a left and right hand endpoint here. If the function's not defined in a bigger interval, that technically speaking, the derivative at the endpoints are what are called one-sided derivatives. Don't worry about it, okay? We're not going to be nitpicky about that kind of thing. Before I state the conclusion, it is also worth saying that there's another theorem related to this that says if little f is continuous, a capital F, an antiderivative, will exist. In fact, we'll talk about that on Monday. The second fundamental theorem of calculus in chapter 6 will prove that. Just because capital F exists doesn't mean you can find a nice formula for it, right? It could be a function you never heard of, like Fresnel or something else. Maybe nobody's given it a name, but it exists as an honest-to-goodness, well-defined function that can be approximated with numerical integration, and that can be graphed once you've approximated it for a lot of values of x. But here, what we're interested in is evaluating the definite integral. To evaluate this definite integral, you just do capital F of B minus capital F of A. It's like magic. Find the area between the curve and the axis, the signed area, I should say, positive when it's above, negative when it's below. You just have to find an antiderivative and plug in these numbers and subtract. Amazing. Astonishing. It is amazing that this works. The discovery of this theorem was the key to saying that calculus has now discovered, so to speak, by Newton and Leibniz. Should have remarked, one more remark here, that while this theorem is always true, theorems are always true, it's not always helpful. When would it not be helpful? It would not be helpful if you could not find a formula for capital F, and we have seen examples of that, like I just mentioned. It's still true, just not helpful. Okay. Still worth talking about, though. We can still use it plenty of times here. There is another version of this that is sometimes called the total change theorem. I'm going to put that in quotes. Total change theorem, because I'm not going to really write it as a theorem. That's why I'm putting it in quotes. And not everybody calls it this. Essentially, I'm just going to write this equation in another way. In a way that makes its truth, dare I say, obvious? Huh? How could this ever be obvious? It is to practitioners of calculus if you think about it in the right way. But just because it's obvious to them doesn't mean they've proved it. Got that? Doesn't mean they proved it. First, a little bit of notation. I'm going to let y be capital F of x. I'm not going to write this as a theorem. I'm just going to write down an equation now. I'm interested in the change in y, which could also be written as the change in capital F. Either one of these notations is okay. I'm interested in finding the change in a function, the change in a quantity, if you prefer, over some interval of time, like the displacement, change in position. Or if the original function I was integrating represented flow rate, like with the tank, this would be the change in volume. To find the change in the function over the interval, which technically, yes, that is capital F of B minus capital F of A. How do you find that total big change? You have to integrate the little changes. Add them up. Leibniz and many even people today, not mathematicians, but you could say maybe applied mathematicians, scientists, engineers, etc., business people who know calculus, they think about that intuitively in terms of a conceptual equation. Here's one of those conceptual equations we talked about last time. It's not a literal equals. It's more of an idea. To find the total change in the function, add up the little changes. Integrate means add. The little infinitesimal changes. The dy represents infinitesimal changes. Infinitesimal changes. It's not a literal equals because this symbol is seemingly not a number. It's more of an idea. Add up the little changes. These dy's are infinitesimally small. This integral sign is adding infinitely many, infinitely small things. Yes, that's what we imagine it to be. Not literally. It's a convenient fiction. I'm trying to give you insight into what your science professors are doing. They are thinking about it that way. I didn't realize that when I was in your shoes. I'm like, how do you know you can do that, right? Like, it makes sense. That's what they say. They don't know how to do proofs of these things. It's okay. I don't, I'm not mad at them that they can't prove things like this. I'm happy that they can apply calculus, okay? Here's another conceptual equation that this equals, well, something you actually can compute. A definite integral. What is dy? How about capital F prime? What should I call the variable? How about t? Capital F prime of t dt. Where dt represents infinitesimal changes as well. dt is an infinitesimal change in time. dy is an infinitesimal change in y, which could be a displacement or a volume, or an amount of money if it was a flow rate for an amount of money. T, I'm using t here instead of x because I'm imagining it to be time. The equality between dy and f prime of t dt could be thought of a couple ways. You could think of the fact that dy dt equals f prime of t as being equivalent to, pretending this is a fraction, dy equals f prime of t dt, and pretending that you're doing a multiplication there. Or here. Are you really doing a multiplication? No. Just pretend. Technically, dt is just telling you, hey, the variable's t, integrate with respect to t. But Leibniz and other people pretend it's a multiplication. The units help as well, right? If it's displacement, this could be meters per second. This could be seconds. The seconds would cancel, giving you meters. An infinitesimal amount of change in meters. These two conceptual equations together amazingly give you an actual equation. So I got a curved equal sign here. Actual equality. Actual equal. Do people typically teach this stuff this way? Not necessarily. I'm trying to give you insight and do sort of mildly humorous things to make you smile. A few people are smiling. You don't need this necessarily for the homework, but it helps you understand. But it does take a while for it to really sink in. So we keep practicing, especially in chapter 8. Define the total change, add up the little change. That's why the fundamental theorem of calculus is true. Right? That's what makes sense to them. Of course, I also could relate this to little f. Capital F prime of t equals little f of t. So I could also write this. This equation, dy equals f prime of t dt, is like distance equals rate times time. If the derivative is speed, distance equals rate times time. A lot of calculus is a generalization of that equation. Distance equals rate times time. Oh, all right, now let's go through a bunch of properties that you should know from chapter 5 that I haven't. Well, the first property I have mentioned, but then the ones I'm going to write down afterwards I have not mentioned yet. More properties. I'm just going to bullet these instead of numbering them. This property we've already mentioned, that the integral of a linear combination like this is the corresponding linear combination with the same constants, but now in front of the integrals of all the individual integrals. Fundamental property of integrals, I call this linearity, and a lot of other mathematicians call it linearity as well. Scientists will often call it superposition. This works for derivatives as well as integrals. Very similar kind of property. The derivative of a summation like this is the corresponding summation of the derivatives. You do that anytime you take a derivative of a long polynomial without thinking about it. That's a theorem. Technically, to prove that, it's not easy because you got to use the more abstract definition of Riemann sums and limits of Riemann sums, and it's a senior math major proof. It's not easy. The next two properties are not theorems, they are definitions. What's the difference? This has got to be proved to be true based on simpler ideas, oh, simpler is relative, doesn't mean it's easy. What I'm about to write are a couple equations that are true because we say so, because it makes sense. We define them to be true. The integral from a to a, what would make sense? The integral is degenerate. It's just a point. I'm trying to find the area of a line. Lines have no area. It makes sense to define the answer to be 0. And that's what we do. And that is handy sometimes to know. Next property is also handy sometimes. What if I switch the a and the b around? What if I put a b down there and an a up here? And what if a truly is still less than b? Well, it's the opposite of the integral where the a is in the bottom and the b is at the top. This is not something to prove, it's a definition. Definitions are true because we say so, though they should make sense. It should be a good idea to define this to be true. If the variable was time and f of t were a velocity, and I'm doing, say, left-right motion, maybe the integral as time goes forward, as I move to the right and then back to the left, is positive. So my change in position is, say, 1 meter in the positive direction. If you videotape me while I did that, and then you watch me walk in reverse, I'd go back like this, and my change in position as time went backwards would be -1. That's what this is saying. The change in position as time goes backwards is the opposite of the change in position as time goes forwards. In that context, that's why this would make sense. And it makes sense in other contexts as well. Next property is that the integral of a function from a to b can be broken up into the sum of two integrals, integral from a to c plus the integral from c to b. This is not a definition. This is a theorem. This takes proof. But we're not going to prove it. But we should make sure it makes sense to us with a picture. If our function looks like that, and say c is between a and b, maybe right there, what this is saying is the total area under the curve is the sum of these two areas. You're splitting up the total area into the sum of two individual areas. Why might you want to do this? Well, it's commonly used when your function is piecewise. Maybe it has a certain formula when x is between a and c, and another formula when x is between c and b. You want to find the total integral from a to b. It might be easier to integrate each piece of the function than add the results. It makes good sense when your graph's above the axis and when c is between a and b, but this formula still works even if the graph goes below the axis or both above and below. And it also even works if c is less than a or bigger than b. Though in those cases, you have to use this fact right there to help you believe it works, to see why it works. If you like abstract math, that's a little bonus exercise for you over the weekend, is to figure out why it works, even if c is less than a or bigger than b. If you don't like abstract math, don't worry about it, but you should know this is true. Again, these kinds of properties come up on my Calculus 1 final exam review video, and I could put properties where you need to use these on your mini exam. Next property, if f of x is even, an even function such as x squared, even power, x to the fourth. More importantly, the graph's got symmetry across the vertical y-axis. That means also that the cosine function is even. If f of x is even, and I'm integrating f of x over some interval centered at 0, say from -a to a, because of the symmetry, this is the same as doing 2 times the integral from 0 to a. Draw a generic picture to illustrate this. Maybe the graph to the right of the y-axis looks like this. Here's A. If this is going to be even, the graph to the left of the y-axis has got to look like this. And this would be negative A. We're trying to find the area under the curve from negative A to A. I can split that into pieces, and by symmetry, the entire area is double the area of any one piece. That's what this is saying. Symbolically, f of x being even means f of negative x equals f of x for all x. It's telling you if you reflect this graph across the vertical axis, you get the exact same graph. If f of x is an odd function, it's even better. Then the integral from negative a to a over an interval centered at 0 is always 0. You don't even have to do any work. Wow, that sounds like maybe the best property of all. Odd functions have what's called origin symmetry. If the graph to the right of the x-axis looks like this, then the graph to the left of the x-axis is going to look about like this. Given any point over here, to find the corresponding point over here, you have to go through the origin, a reflection through the origin like that. And the areas are canceling out. That's a positive contribution. This is a negative contribution. And they're the same area as a positive area, but contributing to the integral, they cancel each other out to give you 0. Symbolically odd means f of negative x equals negative f of x for all x. That happens, for example, with x cubed or x to the 5th or x cubed plus x to the 5th. It also happens for the sine function. You're saying if you reflect the graph across the vertical axis, you get the same graph as if you reflect it across the horizontal axis. These are useful, very, very useful for what's called Fourier analysis. Yes, also Fourier series. Super important topic in advanced science. Also practically important topic for example, communications. Anything with an analog signal, you want to use Fourier analysis to understand and be able to decode the signal for the purpose of, for example, broadcasting something on your speaker. Next property is useful for estimation. If your function f of x is always between two numbers, call them little m and capital M for all x in the interval from a to b, then the integral of f of x is going to also be between two numbers. Little m times b minus a and capital M times b minus a. Like this. Once again, this takes proof, but we will not prove it. However, if you think about a visual example, you should say, hey, it makes sense. Maybe there's f of x. Here's a, here's b. What are little m and capital M? They could be infinitely many different things. If I take little m to be the best lower bound of the function, it will equal the minimum value of the function. That will work. And what we're saying is the area under the curve, the red area, is less than the area, or excuse me, greater than the area of this rectangle. Base is b minus a. Height is little m. Yeah, makes sense. On the other hand, capital M could be a best upper bound for f. It could be the maximum value. This could be capital M. And if we make a rectangle whose area, or whose height is capital M, then capital M times b minus a will be the area of that rectangle, and that'll be bigger than the area under the curve. It's useful for giving rough estimates of integrals when your function doesn't change too much. Next thing is something we've already talked about, average value. Just for re-emphasis, I want you to know it. Average value of f over the interval from a to b. By definition, this is 1 over b minus a times the integral of the function. This is not necessarily standard notation. I like it because it reminds me of statistics to put a bar over the f here. Realize, though, this is not a function. F bar is a number, not a function. It equals the integral divided by b minus a. Both of those things are numbers. So this has got to be a number. Also remember it's equivalent to saying f bar times b minus a equals the value of the integral. That's an f bar times b minus a. And that can be interpreted geometrically as well. Let's do it. We did it for a concave up graph before. This time let's do it for a concave down graph. Here's a, here's b. F of a is there. F of b is here. What we're really after is we're after a rectangle height where the area of the rectangle, base times height, is the same as the area under the curve. If the graph's concave down like this, f bar is going to be closer to the high value than it is to the low value. It might be right about there. It's not halfway between them, unless the graph happens to be a straight line or some slight modification of a straight line. It could happen to turn out by accident sometimes. But if it's concave up or concave down, it will not be halfway between them. If I draw a rectangle about like, well, okay, not doing a perfect job here. About like that, the area of the rectangle is the same as the area under the curve. Set average value is useful for one thing, for understanding concepts in multivariable calculus better. There is also a theorem that I am going to mention that's related to this. It's called the mean value theorem for integrals. MVT for integrals, not that you learn in Calc 1 here. If f is a nice function, I'm not going to write out the theorem completely here. If f is a nice function, meaning continuous on the interval, essentially this says, this says there exists a c in the interval from a to b such that f of c equals f bar. Why am I saying essentially? Again, because I didn't really write this as a theorem. The hypotheses are if little f is continuous on the closed interval from a to b, then there will exist a c between a and b where this is true. In this particular picture, the c would be the value of x where the output equals f bar right there. Where is this useful? One place it's useful is in a subject called numerical analysis, in coming up with numerical schemes to approximate things like integrals, for example. These kinds of facts help you determine methods and bounds for the errors of those methods. One final thing before we do some integration by parts example is called the triangle inequality. Though I will not draw any triangles. The triangle inequality says that the absolute value of the integral, I have to write small here, is less than or equal to the integral of the absolute value. I'm not going to explain why that's called the triangle inequality. There is good reason for it. That's sometimes useful as well. These last two things are not in the book, but I wanted to mention them